This is measuring the charge to mass ratio of an electron, and this was done by J.J. Thomson in 1897. The value is 1.76 times 10 to the 11 coulombs per kilogram. And incidentally, he also found out it was negative. In this particular case, we have a stream of electrons moving through a potential difference. That'll give it kinetic energy. So the kinetic energy is equal to the electron to the voltage difference. That'll be 1/2 mv squared. So if we rewrite this, the speed squared is 2 times the charge times the voltage over the mass. A magnetic field forces the electrons to move in a circle, so in that case the force would be equal to the charge on the electron times the speed times the magnetic field. That would be equal to mv squared over r, because the magnetic field force is acting as a radial force. So if we look at this then and do some math, the charge times the magnetic field would equal mv over r. We square both sides. We have the charge squared, the magnetic field squared is equal to the mass squared times the speed squared over the radius squared. By substitution in for v squared, we get 2 times the charge times the voltage over the mass times the radius squared. Therefore, the charge to mass ratio is equal to 2 times the voltage divided by the magnetic field squared times the radius squared. Now we need to take a look at how we get the magnetic field. Essentially, this is based on the perpendicular bisector of a loop of current and multiplied by the number of turns. So we're looking for a Helmholtz coil that has basically 2 sides here, and at the center we're going to produce a magnetic field where the magnetic field is fairly constant, so we can do this experiment. So the magnetic field is a function of the permeability of free space times the number of turns times the current times the radius squared divided by the radius squared plus x squared, the distance wherever you happen to be between, raised to the 3/2 power. If we assume that x is equal to, did I mess that up? Oh, wrong way. Sorry. X is equal to r over 2. We get the permeability of free space, the number of turns, the current, over 1.25 to the 3/2 times the radius. Plugging in the values for what our Helmholtz coil happens to be, we get that the magnetic field is 7.8 times 10 to the -4 Teslas per amp times whatever current we have. So we can see here that the magnetic field goes up, the radius is going to go down if the voltage is fixed. If the current is fixed, the voltage will go up as the radius goes down, because this is a fixed value. So what we're going to solve for is the charge to mass ratio by varying the voltage and the current 5 times each.